And the latest visitor, the one that now glides silently toward the heart of our solar system, is challenging everything we thought we knew about the cosmos. It is called 3I divided by Atlas, and it presents us with a paradox so profound it feels less like an astronomical observation and more like a riddle posed by the universe itself. It begins with a number so large it borders on the abstract. 33 trillion kilograms. That is the minimum mass. The conservative floor that astronomers have been forced to assign to this interstellar traveler. To grant that figure some earthly meaning, consider the Empire State Building, that steel and stone monument to human ambition. 3I divided by Atlas outweighs it by a factor of 40,000. It is a cosmic heavyweight, a mountain adrift in the void. And yet, this is not the strangest thing about it. The true mystery lies not in its immense size, but in its impossible grace. We see it breathing. Through our most powerful telescopes, we can resolve the ghostly breath of this object, active jets of gas and dust erupting from its surface as it warms in the distant light of our Sunday. Water vapor, carbon dioxide, a cocktail of frozen volatiles sublimating into space, creating a visible, active display that tells us this should behave like a comet, but it doesn't. Its motion is a study in serene indifference. The outgassing we can plainly see, this plume of its own substance being vented into space, should be pushing it. It is a simple and fundamental law of physics, the same principle that propels our rockets to the moon. For every action, there is an equal and opposite reaction. When a comet vents gas, that escaping gas creates a tiny, persistent nudge, a non-gravitational acceleration that subtly alters its path over millions of kilometers. We have measured this rocket effect in countless comets from our own solar system. It is predictable. It is reliable. It is celestial mechanics 101. With 3I divided by Atlas, however, the nudge isn't there. It's like watching a freight train being powered by birthday candles. It glides through space, producing this visible exhaust, yet showing virtually no orbital deviation from its own propulsion. It refuses to be moved by its own breath. Physics is unforgiving in this respect. It adheres to a strict budget of cause and effect, a perfect accounting of momentum. If you expel mass in one direction, the body you expelled it from must move in the other. There is no exception. A comet is, in essence, a leaky celestial boiler. As it gets warmer, ice turns directly into gas, building pressure until it erupts from a fissure or a weak point on the surface. These jets, these fountains of gas and dust, act like tiny thrusters. We have seen this countless times. It's a beautiful, messy, and wonderfully predictable process. The forces are minuscule, yes, but over the course of weeks and months they accumulate. They produce a deviation from a purely gravitational orbit that our instruments are more than sensitive enough to detect. With 3I divided by Atlas, the data is exquisite. We have thousands of positional measurements from hundreds of observatories. The trajectory is known with astonishing precision, and that trajectory is stubbornly, impossibly clean. The math tells us it is moving as if the jets of gas we can see with our own eyes simply do not exist, and my job is to trust the observation. The data does not lie. We pointed the James Webb Space Telescope at this object. We saw the chemical fingerprints of water, of carbon monoxide, and most tellingly, a vast and surprising abundance of carbon dioxide. This is not a guess. This is not an inference. It is a direct measurement of active, ongoing sublimation. We can even estimate the volume of material being lost, roughly 150 kilograms every single second. Imagine 2 people worth of mass, vanishing into space, every second of every day. That is a substantial amount of momentum being carried away from the object. That momentum has to come from somewhere. The comet's nucleus must provide the equal and opposite push. But when we look at the positional data, the residuals, which are the tiny differences between where the object is and where gravity alone says it should be, are flat. They are statistically indistinguishable from zero. This leads us to a collision of two undeniable facts. Fact 1. The object is visibly active, producing a significant gaseous outflow. Fact 2. The object's trajectory shows no measurable reaction to that outflow. When two facts are in direct opposition, it means an underlying assumption is fundamentally wrong, and the only assumption left to question is our initial estimate of the object's inertia, its resistance to being moved. The only way for an object to endure a persistent push without budging is if it is titanically, preposterously massive. The weak push plus the visible activity equals big mass. Very big mass. The 33 trillion kilogram figure is not a wild guess. It is the mathematical consequence of this paradox. It is the minimum mass required for an object to absorb the recoil of its own outgassing and not flinch. It is a lower limit, and the reality could be even more staggering. To truly appreciate how strange this is, we must look at its predecessors. Our first confirmed interstellar visitor, ʻOumuamua, discovered in 2017, was the opposite problem. It was an enigma that showed a measurable non-gravitational acceleration, a definite nudge, but with no visible outgassing at all. There was no coma, no tail. It was a ghost pushing itself through space. Scientists proposed all manner of explanations, from invisible hydrogen gas to it being a thin solar sail of artificial origin. The debate still rages today. Then, in 2019, came 2I, divided by Borisov. Borisov was a relief. It was reassuring in its familiarity. It looked like a comet. It acted like a comet. It had a visible coma and tail, and its non-gravitational acceleration matched the expectations for an object of its size perfectly. It was a textbook small comet, a comfortable, predictable proof that interstellar comets could behave just like our homegrown ones. It suggested ʻOumuamua was the weird one, and Borisov was the norm. And now, there is 3I divided by Atlas. It does not fit either category. It introduces something entirely new, a third class of visitor. It has the visible activity of Borisov, but it has the orbital serenity of a dead rock. It combines the features of both previous visitors in a way that makes no physical sense under our current models. It has the activity of a comet, but shrugs off its own breath like a mountain ignoring the morning mist. We are looking at a regime of physics we have never seen before. We have found dozens of comets in our own solar system, some small, some large. They all fall along a predictable spectrum of behavior. Mass, activity, and non-gravitational push are all linked in a reliable relationship. 3I divided by Atlas exists in an empty space on that chart, a lone data point in uncharted territory. When the initial analysis from Harvard's Center for Astrophysics was circulated, it sent a shockwave through the astronomical community. It was a mixture of profound excitement and deep professional skepticism. That is the proper scientific response to an extraordinary claim. The numbers were checked. The observations were cross-referenced. The underlying physics was debated in forums and video calls connecting researchers across the globe. But the data held firm. More than 4,000 positional measurements from 227 observatories worldwide all told the same silent story. This visitor was different. This visitor was a giant, and its discovery raised an uncomfortable question that cuts to the core of our understanding of the galaxy. Given its size, population models suggest we should have found dozens, if not hundreds, of smaller objects like Borisov before ever encountering a giant like Atlas. We did not. It is like discovering the existence of mice by finding an elephant first. Either our understanding of cosmic debris is fundamentally wrong, or we are witnessing something that challenges the very nature of what drifts between the stars. And this forces us to confront a humbling thought. As we stare at this silent, massive visitor from an unknown star, we must face the most profound question of all. What else haven't we discovered yet? What other titans are gliding through the darkness, waiting to be found? To truly comprehend the enigma of 3I divided by Atlas, we must move beyond its initial shock and delve into the unyielding laws of physics that it appears to so effortlessly defy. The moniker it has earned in astronomical circles, the silent giant, is not a poetic flourish. It is a literal description of the profound contradiction at the heart of its existence. It is an object that is actively, visibly speaking, yet its voice produces no echo in the fabric of space-time. The story of this giant begins with one of the most basic principles of motion, a concept we understand intuitively every time we watch a sprinkler spin on a lawn. As water shoots from the arms of the sprinkler, the escaping liquid creates a tiny force, a recoil that causes the device to rotate. Comets operate on precisely the same principle. The jets of sublimating ice and gas that erupt from their surfaces are not merely for show. They are engines, creating small but persistent pushes that, over time, measurably alter the comet's path through the solar system. We call this non-gravitational acceleration, and for virtually every active comet we have ever studied, it is a standard, predictable feature of its journey. 3I divided by Atlas breaks this pattern completely. Despite the overwhelming evidence of its outgassing, the water vapor streaming away at hundreds of meters per second, the carbon dioxide creating a vast extended coma, the expected orbital nudge simply is not there. The precision of this measurement is difficult to overstate. After analyzing 4,222 distinct positional measurements from a global network of 227 observatories, scientists have been able to place an incredibly stringent upper limit on this non-gravitational acceleration. That limit sits below 15 micrometers per second squared. To put that number into perspective, it is a force so small it is roughly 1/10,000,000th the acceleration you would feel in a gently moving elevator. Our instruments, our mathematics, and our collective observational power have become so precise that we can detect a push that is almost indistinguishable from zero. And yet, what we have found is nothing. The object's motion is, for all intents and purposes, pure. It is moving as if shaped by gravity alone, a silent dance with the sun, completely unperturbed by the violent activity occurring on its own surface. This silence becomes all the more profound when we place 3I divided by Atlas in the context of its interstellar predecessors. Our first visitor, ʻOumuamua, was a puzzle box of its own. It was an enigmatic, fast-moving object, perhaps shaped like a cigar or a flat pancake, that exhibited a clear and measurable non-gravitational acceleration. It was being pushed, but unlike Atlas, it showed no visible cometary activity whatsoever. There was no coma, no tail, not a hint of dust or gas. It was the opposite problem. Scientists were left to grapple with a ghostly push from an invisible engine. The theories were exotic, ranging from the outgassing of pure hydrogen, which would be invisible to our telescopes, to the more sensational hypothesis that it was an object propelled by solar radiation pressure, an artifact, of an extraterrestrial civilization. ʻOumuamua left us with a deep sense of mystery and the unsettling realization that the interstellar medium could send us objects that did not conform to our expectations. Then came our second visitor, 2I divided by Borisov, and with it, a collective sigh of relief from the astronomical community. Borisov was comfortingly, wonderfully normal. Discovered in 2019, it behaved exactly like the thousands of comets born within our own solar system. Its nucleus was about 1 kilometer across, and as it approached the Sun, it grew a magnificent coma and tail. Spectroscopy revealed familiar chemistry, the expected signatures of water and carbon monoxide, and most importantly, its non-gravitational acceleration, the tiny push from its outgassing, matched the predictions of our models perfectly. Borisov was the proof we needed that our understanding of comets was sound, and that these principles could apply to visitors from other stars. It suggested that ʻOumuamua was a strange outlier, and that the galaxy was largely populated by objects we could understand. 3I divided by Atlas shatters that comfortable assumption. It does not fit the mold of the silent pusher like ʻOumuamua, nor the mold of the normal comet like Borisov. It occupies a region of possibility we did not even know existed. One can imagine a chart plotting all known cometary objects. Along one axis, you have the object's mass. Along the other, the amount of non-gravitational acceleration it exhibits. The comets of our solar system would all cluster in a predictable band. For a given level of activity, the larger the mass, the smaller the acceleration. 2I divided by Borisov would fall neatly within this cluster, a familiar cousin from a distant home. ʻOumuamua would be in a lonely corner of its own, an object with high acceleration but no visible gas to explain it. But 3I divided by Atlas would reside in a vast, empty expanse on this diagram, a point of immense mass combined with virtually zero acceleration, despite having visible activity comparable to many objects within the main cluster. It is an object that logically should not exist according to the patterns we have established. It behaves like a massive object that just happens to be sublimating ice, rather than an icy object that happens to be massive. Adding another layer of profound strangeness to this physical paradox is the object's chemical fingerprint, a message from its birthplace carried across millions of years of interstellar travel. The James Webb Space Telescope's near-infrared spectrograph did more than just confirm the presence of gas. It analyzed its composition. The results were startling. 3I divided by Atlas is overwhelmingly rich in carbon dioxide. The ratio of carbon dioxide to water is among the highest ever measured in any comet at this distance from the Sunday. This is not a trivial detail. This chemical signature is a form of cosmic archaeology. It tells us that this object was born in the truly frigid outer reaches of its parent solar system, a region far beyond what astronomers call the carbon dioxide snowline. This is a zone so cold that carbon dioxide freezes solid just as readily as water, at temperatures below -125 degrees Celsius. Most comets in our own solar system formed closer in regions where water ice was the dominant building block. 3I divided by Atlas, therefore, carries the frozen memory of truly alien conditions, a chemical portrait of a stellar environment very different from our own. And the scale of this carbon dioxide production is immense. It is not just a trace component. Observations from the Sphere-X space-based infrared telescope revealed an extended carbon dioxide coma stretching for hundreds of thousands of kilometers from the nucleus. This means that the relatively compact, bright object we see in visible light telescopes is just the heart of a much larger, more substantial and largely invisible atmosphere of gas surrounding the solid core. This massive, invisible envelope reinforces the paradox. It is undeniable proof of enormous amounts of gas escaping the object, which makes the lack of a corresponding recoil all the more baffling. The physics of the situation becomes deeply uncomfortable. The laws of momentum conservation are not optional suggestions. They are fundamental to the workings of the universe. Gas escaping at hundreds of meters per second carries momentum, and that momentum must be transferred to the parent body. A typical 1-kilometer nucleus experiencing this level of gas loss would show an acceleration that is easily detectable by our precision instruments. Yet, the 4 months of continuous data covering the exact period when this cometary activity was ramping up show residuals consistent with pure, unadulterated gravitational motion. This is where the detective work of astrophysics becomes a matter of striking, straightforward math. The data from the spectrographs gives us the velocity of the escaping gas, estimated to be around 440 meters per second, a typical speed for sublimating volatiles. The brightness and composition data allow us to calculate the mass loss rate, the aforementioned 150 kilograms per second. When you know how much material is leaving and how fast it is going, you can calculate the precise force of the recoil. It is a simple equation. And when you compare that predicted force to the observed acceleration of nearly zero, you are forced into an unavoidable conclusion. The only way to reconcile the powerful push with the lack of movement is to invoke an incredible amount of mass. The object must be so heavy that the constant thrust from its jets is too feeble to register. Using typical comet densities of about 500 kilograms per cubic meter, the 33 billion ton lower mass limit corresponds to a nucleus at least 5 kilometers in diameter. This is genuinely enormous by the standards of interstellar visitors. To place this in perspective, ʻOumuamua was likely less than a kilometer in its longest dimension, and may have weighed a few million tons. 2I divided by Borisov had a nucleus of about 1 kilometer, and contained perhaps a few billion tons of material. 3I divided by Atlas potentially outweighs both previous visitors, combined by a factor of 10 or 1,000, a true heavyweight in a field previously thought to be dominated by lightweights. It looks like a comet, it breathes like a comet, but it shrugs off its own breath like a boulder. This profound disconnect between its appearance and its dynamics forces us to ask an uncomfortable question. What are we really looking at? The silent giant is masquerading as an ordinary comet, but the relentless application of physics has revealed its true nature, that of an anomalously, mysteriously, and paradigm-shatteringly massive object. This is just the first layer of a complex cosmic puzzle. How were we able to obtain measurements of such astonishing precision? And what other secrets is it hiding in its paradoxical appearance and alien chemical composition? If this cosmic detective story fascinates you as much as it does us, and you want to follow along as we piece together the next clues in the investigation, make sure you are subscribed and have notifications turned on. The mystery of 3I divided by Atlas is just beginning to unfold, and you will not want to miss what comes next. An object is discovered not by a person, but by an algorithm. In the cold, thin air of the Chilean Andes, a robotic telescope dutifully scans its assigned patch of the southern sky, capturing vast swathes of stars in wide-field images. It is one eye in a network named Atlas, the asteroid terrestrial impact last alert system. Its primary task is a solemn one: to search for asteroids that might pose a threat to Earth. On the night of July 1st, 2025, it captures another image, one among millions, and in that image software detects a faint, anonymous point of light that was not there in previous frames. It is a single, unremarkable dot on a digital sensor, a whisper in a sea of cosmic noise. On its own, this dot means nothing. It could be an instrumental artifact, a cosmic ray strike, a known asteroid. But the system is designed to remember. It cross-references the new dot with catalogues of millions of known objects and finds no match. It flags the anomaly, and with that single automated act, a global investigation of unprecedented scale begins. A single point of light is not a story, it is a question. To transform that question into a narrative, you need more points. You need to connect the dots across time. The initial flag from the Minor Planet Center, the world's clearinghouse for all such discoveries, acts as a celestial call to arms. The message spreads through professional and amateur networks with the speed of light. A new object of interest, its orbit still highly uncertain, has been found. And so, the great eye of planet Earth begins to open. This is not a single instrument, but a distributed planetary-scale observatory comprised of hundreds of individual facilities, each one a vital component in a global symphony of observation. As the Earth spins on its axis, the view from Chile sets below the western horizon. But in the deepening twilight of Arizona, or atop the volcanic peak of Mauna Kea in Hawaii, another set of eyes takes over the watch. As darkness falls over the Canary Islands and Europe, their telescopes join the pursuit. And then, the observatories in Asia and Australia pick up the thread. It is a continuous, 24-hour-a-day, 7-day-a-week relay race, a seamless passing of a baton of light from one continent to the next, all chasing a single, faint traveler. What these hundreds of telescopes are performing is a science known as astrometry. It is one of the oldest branches of astronomy, yet it has been revolutionized in the digital age. In essence, astrometry is the art and science of measuring, with excruciating precision, the positions of things in the sky. It is cosmic detective work at its most fundamental level. Each observatory that points its mirror at 3I divided by Atlas does not just take a pretty picture. It performs a rigorous measurement. The image is captured, and the exact celestial coordinates of the object, its right ascension and declination, are calculated by referencing its position against the fixed backdrop of distant stars and galaxies, whose locations are known to an incredible degree of accuracy. Each of these measurements is a single clue, a single frame in the long exposure photograph of the object's motion. String enough of these frames together, and a pattern emerges. You can trace its path, calculate its orbit, and predict where it will be tomorrow, next week, or next year. But the true power of this global network lies in its ability to detect not just the path itself, but the almost imperceptible deviations from that path. The precision required to do this staggers the imagination. We are attempting to measure positional shifts that are smaller than 1/28,000th of an arcsecond. To give that a physical scale, it is equivalent to detecting the width of a single human hair from a distance of 20 kilometers. This feat is not achieved through a single miraculous measurement. It is the result of statistical power. Each of the 4,222 measurements contributed to the analysis of 3I divided by Atlas carries its own tiny margin of error. The Earth's atmosphere blurs the light. Telescope optics have microscopic imperfections. Detectors have noise. But by combining thousands of independent measurements from different instruments at different locations, these random errors begin to cancel each other out. The noise fades away, and what is left is a signal of almost pure, unblemished truth about the object's location in space. My work lives in this data. It is a torrent of numbers, of coordinates, of timestamps, all flowing from this global network into central databases. And our task is to make sense of it, to build a model that fits this exquisitely precise data. The first step is to model the effect of gravity alone. We know the mass of the Sun, of Jupiter, of all the major bodies in the solar system, with incredible accuracy. We can use the laws of Newtonian mechanics, refined by Einstein's general relativity, to calculate a perfect, idealized orbit for 3I divided by Atlas. This is the path the object should be following if gravity were the only force acting upon it. Then comes the moment of truth. We take our thousands of real-world observations and we lay them over this perfect, theoretical curve. The difference between where the object actually is and where our gravitational model says it should be is a quantity we call the residual. If a comet is being pushed by its own jets, its residuals will not be zero. They will show a systematic, growing deviation away from the purely gravitational path. With 3I divided by Atlas for 4 solid months, from May 15th to September 23rd, 2025, as its activity was visibly increasing, the residuals remained stubbornly, maddeningly flat. The real-world data points landed so perfectly on the theoretical curve that it was as if they were painted there. This long observational window is the key. A tiny, unnoticeable acceleration can be hidden in the noise of a few observations over a short period. But its effect on position is cumulative, and it grows with the square of time. It is like searching for a microscopic leak in a massive dam. Watching for a minute, you would see nothing. But if you watch for months, even the tiniest trickle will eventually create a noticeable puddle. An acceleration of a few micrometers per second squared, sustained over a period of more than 120 days, should have produced a positional deviation of thousands of kilometers. This would not be a subtle effect. It would be a glaring, obvious, unmissable signal in the data. It would be a fire alarm shrieking in a library. But all we heard was silence. All the global eye saw was an object moving with a serenity that defied the visible evidence of its own turmoil. This was not a failure of our instruments. On the contrary, it was one of the greatest triumphs of observational astronomy. The global network did not fail to find the non-gravitational acceleration. It succeeded, with unprecedented certainty, in proving its almost complete absence. It placed the tightest constraints ever achieved for such an active object. This null result was not an empty finding. It was a powerful, profound piece of evidence in its own right. It was the crucial clue that transformed the puzzle of 3I divided by Atlas from a curiosity into a fundamental paradox. This level of precision requires a detective story approach, stitching thousands of pinpricks of light into a trajectory so tightly constrained that it could be used to test fundamental physics. Each observatory, from the professional behemoths to the dedicated amateur collaborations, contributed a piece of the puzzle. The amateur astronomers, while perhaps having less precise instruments individually, provided crucial temporal coverage, filling in the gaps, and characterizing how the object's brightness evolved night after night, as it warmed on its approach to the Sunday. This is modern astronomy at its collaborative best. It is a system where data flows freely, where discovery is a shared enterprise, and where the planet itself is turned into the baseline of a single, colossal telescope. The speed of the process is a testament to our modern capabilities. In historical times, confirming the orbit of a new comet could take months or even years of painstaking manual calculations. 3I divided by Atlas went from its first detection as an anonymous dot to having its interstellar nature and its anomalous dynamics characterized in a matter of weeks. Automated detection algorithms, rapid communication networks, and immense computing power have compressed discovery timelines that once stretched across entire seasons. The global eye network that watched 3i divided by Atlas represents a new era in our ability to scrutinize the cosmos. It has provided the evidence, the hard numbers that ground the mystery, and the evidence is unambiguous. We are faced with an object that, according to the most precise measurements humanity can make, is a silent giant. And now, we must confront the staggering implications of what that truly means. If the motion of 3i divided by Atlas was a riddle written in the silent language of gravitational mathematics, its appearance was a paradox, painted in visible light. On July 21st, 2025, after weeks of tracking the object as a mere point of light, the Hubble Space Telescope was given the task of capturing its portrait. Astronomers around the world waited for the data to download, anticipating the familiar, comforting sight of a comet. A bright, condensed nucleus, followed by a gossamer tail of dust and gas, swept back and away from the Sunday. It is one of the most reliable and iconic visuals in all of astronomy, a celestial weather vane faithfully indicating the direction of the solar wind. For centuries, ancient Chinese astronomers used the orientation of comet tails as celestial compasses. They are predictable. They are understood. What Hubble sent back, however, was something else entirely. It was an image that stopped astronomers in their tracks, an image that defied basic intuition. Instead of the classic comet shape, 3i divided by Atlas displayed what observers could only describe as a teardrop-shaped cocoon of light. And from this cocoon emanated a pronounced, unmistakable sunward glow. A significant portion of its visible coma, the very material being shed from its nucleus, was pointing not away from our star, but directly towards it. It was like watching smoke refuse to rise from a fire, or seeing the wake of a boat appear in front of the bow. The brain rebels against the image, because it violates a lifetime of experience with how debris should flow in response to an external force. When you see a tail pointing toward the sun, your mind begins working overtime, racing through the physics textbooks to find a way to reconcile what you are seeing with what you know to be true. To be clear, features that appear to point toward the sun, known as anti-tails, are not completely unprecedented in the study of comets. They are rare, but not unheard of, and they typically have well-understood explanations. The first, and most common, is a simple illusion of perspective. As Earth moves in its orbit, our viewing angle on a comet changes. Sometimes, this geometry can create a line of sight effect, where dust particles that were shed by the comet and are now trailing behind it in its own orbit appear from our specific vantage point to project in the direction of the Sunday. It is a trick of geometry, a temporary alignment that vanishes as our planet continues its journey. The second explanation involves dust dynamics. A comet's tail is a mixture of particles of different sizes. The finest, lightest dust is easily pushed away by the pressure of solar radiation and the solar wind, forming the classic sweeping dust tail. But larger, heavier grains, perhaps the size of pebbles or sand, are not so easily swayed. They have more inertia and tend to follow their own ballistic trajectory, largely ignoring the sun's breath. Their path is still governed by the comet's original orbit, and under the right viewing conditions, this stream of heavier debris can also appear as a sunward-pointing spike. But 3i divided by Atlas refused to fit neatly into these conventional boxes. The sunward glow was not a brief, geometric illusion that disappeared as the Earth and the comet changed their relative positions. Its persistence and its prominence made it notably unusual. Observations from Hubble in July were followed by more in August from the Gemini South Telescope in Chile. The feature remained, This was not a fleeting trick of the light. This suggested a real, ongoing physical process was responsible for this strange, forward-pointing structure. And the portrait was not static. It was evolving. The August observations from Gemini revealed an additional complexity. While the forward-pointing glow remained, a more traditional, anti-solar tail had begun to emerge from the other side. The morphology was changing in real time as the object warmed on its inbound journey. It was as if the object was now wearing two faces, one that obeyed the rules and one that broke them. This evolving, paradoxical appearance has profound implications that ripple back to the core mystery of the silent giant. The science of astrometry, which gave us the object's mass, does not measure the position of the solid nucleus itself. The nucleus is far too small and shrouded in gas to be seen directly. Instead, astrometry measures the position of the photocenter, which is the brightness-weighted average position of the entire fuzzy coma. Now, we must ask a critical question. If the coma has this bizarre, persistent, and asymmetric sunward feature, could it be systematically shifting the apparent center of brightness away from the object's true center of mass? Could this strange portrait be an elaborate mask, creating a subtle astrometric error that is hiding the very non-gravitational acceleration we are looking for? It presents a challenge to the silent giant hypothesis. The puzzle becomes more intricate. To understand the object's mass, we must first understand its light, and its light is behaving in ways we have never seen before. But the portrait of 3I divided by Atlas is more than just its shape and form. It is its composition. To truly understand a painting, one must also analyze the paint. In astronomy, this is done through spectroscopy, the science of dissecting light. A team of astronomers used the Very Large Telescope, another of the world's premier observatories in the Atacama Desert, to capture the spectrum of the object's coma. They were searching for the chemical fingerprints of the elements being released from the nucleus. What they found added a new, deeply perplexing layer to the mystery. The spectra showed multiple, prominent emission lines of the metal nickel, blazing brightly in the infrared. Nickel itself is not entirely unexpected in comets, but it is almost never seen alone. Nickel and iron are cosmic siblings. They are forged together in the hearts of dying stars. Through similar nucleosynthetic processes, they condense into similar mineral compounds in protoplanetary disks. In meteorites and cometary dust, where you find one, you almost invariably find the other. In the spectra from 3I divided by Atlas, the iron was conspicuously absent. The wavelengths where iron lines were expected to appear showed nothing but background noise. This was not a failure to detect a weak signal. The data was sensitive enough to place a very low upper limit on the amount of iron present. The conclusion was inescapable. For some reason, this object was releasing nickel into its coma, but not iron. It is like discovering a forest full of oak trees, but no maple trees, in a region where both species should normally coexist. This chemical asymmetry challenges our basic assumptions about how metals are released from cometary bodies. Some commentators in fringe media immediately leaped to sensational conclusions, noting that certain industrial alloys are rich in nickel but poor in iron, suggesting a technological origin. This represents a logical leap, unsupported by any evidence. The emissions seen are from individual nickel atoms in a gas, a product of well-understood atomic physics, not industrial engineering. The scientific community, instead, focused on finding a natural explanation for this truly unusual, but not necessarily artificial, chemistry. The hypotheses are as exotic as the observation itself. One possibility is a process called photon-stimulated desorption. In this scenario, high-energy ultraviolet photons from the sun are striking the surface of the nucleus, and have just the right energy to break the chemical bonds holding nickel atoms within certain surface compounds, liberating them into the gas phase. The same photons might not be energetic enough to free the more tightly bound iron atoms. Another, perhaps more compelling idea involves the thermal breakdown of exotic organometallic compounds. This hypothesis connects back to the object's cold, carbon dioxide-rich origins. In the ultra-frigid environment where 3I divided by Atlas formed, nickel may have bonded with organic molecules to form volatile complexes that decompose at the relatively low temperatures the nucleus is now experiencing. Iron, meanwhile, might be locked away in more refractory, heat-resistant minerals like silicates, which will not release their metals until the comet gets much closer to the sunday. We are now faced with a series of nested paradoxes. There is the physical paradox of its motion, a giant that refuses to be pushed. There is the morphological paradox of its appearance, a comet with a tail that points the wrong way. And now there is a chemical paradox in its composition, the mystery of the lonely nickel. These are not likely to be independent problems. They are almost certainly interconnected facets of a single, complex truth. The strange, ultra-cold chemistry is likely responsible for the sublimation processes that, in turn, drive the unusual dust dynamics, which create the paradoxical morphology. And that complex morphology may, in some way, be influencing the astrometric measurements that are the foundation of the physical paradox. Every layer we peel back reveals not a simple answer, but a deeper, more intricate question. 3I divided by Atlas seems determined to violate our expectations at every level of analysis, a cosmic enigma that is as beautiful as it is baffling. Imagine, for a moment, that we are explorers of a newly discovered continent. For centuries, we have only been able to see its shores from a distance. But now, armed with new technologies, we have built the first systematic outposts and are beginning to survey its vast, unknown interior. Based on all our knowledge of ecosystems, we have a clear set of expectations. We expect to first encounter the small, the numerous, the common. We anticipate cataloguing countless insects, mapping the territories of small mammals, and documenting the flocks of birds. Only later, after venturing much deeper into this wilderness, would we ever hope to catch a fleeting glimpse of the continent's rarest and most magnificent megafauna, the herds of elephants, the solitary rhinos, the great apes. This is a fundamental law of ecological sampling. You always find the mice before you find the elephants. In the year 2017, humanity began its first true safari into the interstellar wilderness that surrounds our solar system. Our new wide-field survey telescopes became our eyes, methodically scanning the sky for movement, for visitors crossing from the great plains of the galaxy into our local territory. And the results of this safari have been, to put it mildly, deeply unsettling. Our first encounter was with ʻOumuamua, a bizarre, fast-moving creature of indeterminate shape that defied easy categorization. Our second was 2I divided by Borisov, a comfortingly familiar species that behaved exactly as our theories predicted. And our third catch, the colossal 3I divided by Atlas, is the equivalent of our exploration party on its very first major expedition, stumbling directly into a bull elephant of a size and disposition never before imagined. This discovery has created a genuine puzzle that keeps astronomers awake at night, a statistical anomaly so profound that it forces us to question the very maps we are using to explore this new frontier. The problem is one of simple numbers and probabilities. If 3I divided by Atlas truly weighs 33 billion tons or more, with a nucleus spanning 5 kilometers, it represents such an extreme outlier that our basic assumptions about the demographics of interstellar objects might require a fundamental revision. We should have found dozens, or even hundreds, of smaller visitors like Borisov before ever encountering such a massive specimen. Think about it logically. The universe is a messy and chaotic place. Planetary systems are not gentle nurseries. They are violent arenas where gravitational forces constantly reshape destinies. Throughout the galaxy, objects are being thrown out of their home systems through a variety of mechanisms. The most common is thought to be gravitational scattering during the chaotic early phases of planet formation. In this cosmic billiard game, massive planets like Jupiter act as the cue balls, flinging smaller asteroids and comets, the billiard balls, onto hyperbolic escape trajectories. The physics of this process inherently favors the ejection of smaller objects. It simply takes less energy to accelerate a small piece of debris to escape velocity than it does to launch a mountain-sized body into the interstellar void. For every single 5-kilometer object that is successfully ejected, there should be a vast multitude of 1-kilometer objects and an even greater number of 100-meter objects cast out alongside it. The size distribution of material in the interstellar medium should, therefore, be steeply weighted toward the small end. It should be a pyramid, with a vast base of tiny objects and a very narrow peak of large ones. And yet, here we are, with a statistically meaningless sample size of 3 visitors, and the latest one is potentially the largest by far. It is like trying to characterize the height distribution of the entire human race after measuring only 3 randomly selected individuals, one of whom happens to be a 7-foot-tall basketball player. The outlier completely distorts the picture. This uncomfortable implication forces us to explore a series of possibilities, each one a potential solution to the puzzle of the elephants. The first, and perhaps most conservative, is that we are simply dealing with observational selection effects. Perhaps our safari is not as random as we think. Maybe our methods are, for some reason, biased towards spotting the elephants and missing the mice. It seems counterintuitive. Smaller objects should be more numerous and should pass by more frequently. But perhaps larger objects, like 3i divided by Atlas, produce much brighter, more expansive comas as they warm up. This increased brightness would make them detectable from much greater distances, effectively increasing the volume of space in which our surveys could find them. The elephant might be rare, but if it shines a brighter light, it is easier to spot in the dark. Furthermore, we must consider the geometry of the encounter. 3, I divided by Atlas, approached our solar system on a trajectory nearly aligned with the ecliptic plane, the flat disk where all the planets orbit. This is the very region of the sky where our survey telescopes spend most of their time looking. It is possible that there is a hidden swarm of smaller interstellar objects passing through our system at highly inclined, bizarre orbits, and we are simply not looking in the right places to find them yet. We may have found the elephant because it happened to wander directly through the middle of our camp. A second, more intriguing possibility is the fragility hypothesis. This idea proposes that the mice are indeed being created in vast numbers, but they do not survive the journey. The trip between the stars is not a gentle one. It is a grueling marathon that can last for millions, or even tens of millions, of years. During this immense transit time, an object is exposed to the harsh environment of interstellar space. It is perpetually bombarded by high-energy cosmic rays, a constant form of celestial radiation that can erode and break down surface materials. It may pass through interstellar dust clouds, suffering a slow death by 1,000 tiny collisions. It may even experience thermal shocks, being gently warmed and then cooled as it passes by other, distant stars. The fragility hypothesis suggests that these erosive processes preferentially destroy smaller, less gravitationally coherent objects. The mice get sandblasted into dust over the eons. Only the largest, most robust specimens, the elephants, have enough mass and structural integrity to endure the harshness of the interstellar wilderness and arrive at our shores intact. If this is true, the population of objects arriving in our solar system may not be representative of the population that was originally ejected. The interstellar medium itself may act as a great filter, allowing only the giants to pass. The third, and most radical, possibility is that our understanding of the ejection mechanisms themselves is incomplete. We assume that planetary systems are democratic in their ejections, throwing out far more small objects than large ones. But what if some systems are different? What if there are specific stellar environments or events that are uniquely efficient at creating and ejecting massive objects? Perhaps violent instabilities in the massive, debris-rich disks around very young, hot stars can form large planetesimals and fling them into space before they have a chance to coalesce into planets. Perhaps close flybys between stars in the dense stellar nurseries where they are born are more effective at ejecting large bodies than our models currently predict. In this scenario, it is possible that our solar system is currently passing through a stream of debris that originated from one of these hypothetical elephant factories. Our visitor would not be a representative of the galactic average, but a specialist from a very particular and violent type of environment. For now, with a sample size of 3, these ideas remain in the realm of reasoned speculation. We are still at the very beginning of our exploration, but this is about to change. The Vera C. Rubin Observatory, now entering its operational phase in Chile, represents nothing less than a revolution in this field. It is a new kind of eye on the universe, a survey machine of unprecedented power that will scan the entire southern sky every few nights for a decade. It will not discover 1 or 2 interstellar objects. It will discover hundreds, perhaps thousands. The Vera Rubin Observatory will be the ultimate arbiter of this statistical puzzle. It will provide the data we need to move from speculation to certainty. If it reveals a flood of smaller, Borisov-like objects, then we will know that 3I divided by Atlas was just that a magnificent 1 in a million statistical fluke. But if this new, powerful eye begins to find more elephants, if massive objects like 3I divided by Atlas turn out to be even moderately common, then it will signal that a fundamental revision of our theories of planet formation and galactic evolution is upon us. The puzzle of this single object has pushed us to the brink of a new understanding, forcing us to accept that the cosmic wilderness is far stranger and filled with far larger creatures than we ever dared to imagine. To solve the puzzle of the elephants, to understand why our first true interstellar safari has yielded such a colossal specimen, we must look beyond the animal itself and ask a more fundamental question. What kind of wilderness produces such creatures? If the space between the stars is populated by these wandering objects, then what are the factories that build them, and what are the engines that drive their exile? We must journey back in time and across the galaxy to witness the birth and disruption of other solar systems. For every interstellar visitor is a refugee, a piece of a long-lost home, carrying with it the story of its violent expulsion. The galaxy operates like a vast redistribution network for planetary debris, with stellar systems continuously ejecting material into a great, unseen reservoir. Our solar system is currently sailing through this reservoir, and understanding its contents means understanding the 3 primary mechanisms of cosmic exile. Let us travel first to a young solar system, 4 billion years in the past. It is a place of breathtaking chaos and creation. A nascent star blazes at its center, surrounded by a vast, turbulent disk of gas and dust, the raw material of future worlds. Within this disk, gravity is pulling matter together, building the first planetary embryos. One of these grows faster than the others, reaching a critical mass where it can sweep up vast amounts of gas. It becomes a gas giant, a new king establishing its gravitational dominion. Its birth brings a semblance of order, but it is the order of a tyrant. As it migrates through the system, its immense gravity bullies everything in its path. Imagine a small, icy body, a pristine kilometer-scale comet, orbiting its sun in a peaceful, stable ellipse for millennia. But the new giant is on the move. Its orbit shifts, bringing it into a close encounter with the smaller body. The comet is caught. It is pulled into the planet's immense gravity well, not to be consumed, but to be used as a tool in a gravitational slingshot of cosmic proportions. The planet's orbital energy is transferred to the small comet, accelerating it, whipping it around, and flinging it back out into space with such tremendous force that it achieves escape velocity. It is now on a hyperbolic trajectory, a path that will never return. It has been exiled, doomed to wander the great darkness between the stars forever. This is planet-to-planet gravitational scattering, and for decades, we have believed it to be the dominant engine of ejection. It is a cosmic billiard game, and it is incredibly efficient at clearing out the smaller debris, the planetary construction leftovers. But this is also where our models begin to strain. This mechanism works beautifully for the billiard balls, the small, kilometer-scale comets. Launching something with the mass and size of 3I divided by Atlas, however, is like trying to play billiards with a bowling ball. It would require a perfect, high-energy, geometric alignment, a trick shot of such power and precision that it would be an exceedingly rare event. While possible, relying on this mechanism alone makes a visitor, like Atlas, a statistical improbability. So we must look for another engine, a more powerful one. For this, we must change our perspective. Most stars are not born in quiet isolation, but in the crowded, bustling maternity wards of the galaxy we call stellar clusters. Here, hundreds or thousands of stars form in close proximity, each with its own nascent planetary system. Let us imagine our young solar system again, but this time it has a neighbor. Another star, born from the same great cloud of gas, is passing nearby. In human terms, nearby is a meaningless concept. It is still a journey of hundreds of billions of kilometers, but in gravitational terms, it is an intrusion, an act of cosmic theft. Our solar system's outermost realm is a vast, ghostly sphere of trillions of icy bodies, the Oort cloud, all held in a tenuous gravitational embrace by their parent star. They are the most vulnerable members of the solar system family. As the passing star glides by, its own gravity reaches out and tugs on this fragile outer shell. It is a gentle but inexorable pull that disrupts the delicate million-year orbits of these icy bodies. Some are pulled inward to become comets that grace the inner solar system, but many others are pulled outward, perturbed, and given just enough of a gravitational nudge to be set free. They are stolen from their home and cast adrift. This mechanism, a stellar flyby, is a far more plausible candidate for creating massive exiles like 3I divided by Atlas. The gravitational influence of a star is orders of magnitude greater than that of a planet. A close encounter with a star of similar mass to our own could easily provide the energy needed to eject a 5-kilometer body. This process might be less common than the constant grind of planet-to-planet scattering, but it is a factory built for giants. There is a third, even more primordial pathway to exile, one that takes us back to the very dawn of a solar system's existence. We journey further back in time, to the first few million years of the star's life, before the planets have even fully formed. The protoplanetary disk is not a smooth, serene whirlpool. It is a violent, gravitationally unstable sea of matter. It is so massive that its own gravity causes it to collapse into dense, swirling spiral arms, a miniature galaxy in its own right. These structures are not static. They are dynamic, sweeping through the disk, creating shockwaves and turbulence. Embedded within this disk are the first large objects to have formed kilometer-scale planetesimals that are the building blocks of future planets. As the massive spiral density waves propagate through the disk, they act like a gravitational tsunami, scattering these embedded objects with incredible violence. Many are thrown into their central star, but some are ejected outwards with such force that they escape the system entirely. This mechanism, known as disk instability, is a powerful engine for ejecting large bodies, because it acts on them before they have become gravitationally anchored by a fully formed planetary system. However, it operates on a strict time limit. Protoplanetary disks are fleeting phenomena, typically dissipating within 5 to 10 million years due to radiation from the central star. This means that an object like 3I divided by Atlas would have had to both form to its massive size and be ejected within this incredibly short cosmic window, a significant constraint on its origin story. We return to the present day, armed with the knowledge of these 3 great cosmic factories: the relentless billiard game of planetary scattering, the grand larceny of stellar flybys, and the primordial explosions of disk instabilities. The interstellar reservoir problem is the challenge faced by theorists who must now try to combine these processes into a single, coherent model. They must act as cosmic accountants, estimating star formation rates over billions of years, modeling the crowded dynamics of stellar clusters, and calculating the efficiencies of each ejection pathway for objects of all sizes. The goal is to produce a definitive prediction, a census of the interstellar reservoir. How many objects of what size should be passing through our solar system per year, on average? Most current models, which assume planet-to-planet scattering is the dominant process, predict a steep pyramid, where giants like Atlas are exceptionally rare. The very existence of our visitor suggests that this assumption may be wrong. It may be that stellar flybys or disk instabilities are far more significant contributors to the interstellar population than we have ever given them credit for. 3I divided by Atlas, by its very presence, is forcing us to recalibrate our understanding of the galactic ecosystem. Our sample size of 3 is still too small to rewrite the textbooks, but it is more than enough to pose a profound and urgent question. The messenger has arrived, but what message is it carrying about its birth? Its chemistry, rich in carbon dioxide, hints at an origin in the frigid outer disk, a place where stellar flybys and disk instabilities reign supreme. The silent giant is silent no more. It is beginning to speak of its violent, chaotic, and epic origin story. To understand an object like 3I divided by Atlas is to become a forensic scientist. The object itself is the subject. Its coma is the scene of the crime, and the light it emits is the only evidence left behind. Our task is to collect that evidence, bring it back to the lab, and subject it to an interrogation so intense that it reveals its deepest secrets. The laboratory, in this case, is the Atacama Desert in Chile, and the interrogation tool is one of the most powerful instruments ever created by humankind: the Very Large Telescope, or VLT. Its massive mirrors are designed to gather the faintest whispers of light from across the cosmos. But its true power lies not in collection, but in dissection. Attached to the telescope is a high-resolution spectrograph, a device that acts as a cosmic prism, taking the pale, blended light from the comet's coma and splitting it into its constituent wavelengths, its fundamental rainbow of information. Within this rainbow is a hidden code, a series of bright lines and dark gaps that are the unmistakable fingerprints of the chemical elements present at the scene. In August of 2025, astronomers began their interrogation of the light from 3I divided by Atlas. The process is one of meticulous patience. For hours, the VLT's eye remains fixed on its target, gathering every photon it can from the distant, ghostly cloud of gas. This light is then channeled into the spectrograph, where it is spread out into a spectrum of incredible detail. When the data first appeared on the screens of the astronomers analyzing it, it began to tell a story. They saw the expected signatures, the familiar fingerprints of molecules like cyanogen, a common compound found in comets. This was the baseline, the normal part of the story. But then, as they scanned through the infrared portion of the spectrum, a new set of fingerprints appeared. They were sharp, clear, and unambiguous. The analysis software cross-referenced the wavelengths with a vast library of atomic transitions and returned a positive identification: nickel. Not nickel bound in dust grains, but atomic nickel, a glowing gas of pure metal suspended in the coma. This was, in itself, a significant finding. While not entirely unprecedented, seeing metal emissions from a comet so far from the Sun was unusual and exciting. It hinted at a dynamic and complex chemistry at play on the nucleus. But the true mystery was not what the light revealed, but what it concealed. The forensic investigation of the cosmos is often about searching for known accomplices. In the grand narrative of stellar nucleosynthesis, the process that forges heavy elements inside stars, nickel, and iron, are inseparable partners. They are born together in the fiery death throes of supernovae, created in relatively stable ratios, and blasted out into the galaxy to seed the next generation of stars and planets. They condense into similar types of minerals and dust grains. In virtually every cosmic environment we have ever studied, from meteorites that have fallen to Earth to the dust in distant galaxies, where you find an abundance of nickel, you are certain to find an abundance of its partner, iron. They are the chemical twins of the periodic table. Knowing this, the astronomers at the VLT knew exactly where to look in their spectrum. They focused their attention on the specific, well-documented wavelengths where the fingerprints of iron atoms were supposed to be. They expected to see another series of bright, sharp emission lines, confirming the presence of the known accomplice. But there was nothing. Where the bright lines of iron should have been, there was only the flat, featureless terrain of background noise. The astronomers checked their instruments. They recalibrated their data. They ran the analysis again. The result was the same. The silence in the spectrum was as real and as profound as the nickel lines were bright. This was not a case of a weak signal being missed. The spectrograph was more than sensitive enough to detect even trace amounts of iron. The data established a definitive upper limit on its presence, and that limit was shockingly low. The conclusion was as unavoidable as it was bizarre. 3I divided by Atlas was actively releasing significant quantities of nickel gas into its coma, while keeping its iron under lock and key. It is a violation of cosmic chemistry so fundamental that it is like a detective arriving at a crime scene and finding a perfect set of fingerprints from one hand, but discovering that the suspect is physically missing their other hand. It makes no logical sense based on a century of forensic experience. This chemical asymmetry demands an explanation, and as is often the case with such a profound anomaly, it has attracted both sober scientific inquiry and wild speculation. The most sensationalist narratives, amplified by social media and fringe websites, were quick to point out that some human-made industrial alloys, like mu metal, are rich in nickel while being poor in iron. This was presented as a smoking gun for a technological origin. But this line of reasoning is a classic red herring, a misinterpretation of the evidence. We are observing individual atoms of nickel glowing as a gas, a product of low-temperature atomic physics in a near vacuum. We are not observing solid shards of a manufactured object. In science, a genuine mystery is an invitation to refine our understanding of nature, not an automatic proof of the supernatural or the artificial. The universe contains far more natural processes capable of producing unexpected results than our limited imaginations can often conceive. The real forensic work lies in exploring these natural pathways, no matter how exotic they may seem. The first clue in this investigation is the behavior of the nickel itself. As 3I divided by Atlas continued its journey toward the Sun through August and September, astronomers noticed that the brightness of the nickel emission was not constant. It was increasing dramatically, following a steep power law relationship with its distance from the Sunday. This was not a slow, steady leap. This was a chemical process that had been switched on as the object warmed, suggesting it was tied to a specific temperature threshold. It was as if a particular type of ice on the nucleus reached its melting, or in this case, its sublimation point, releasing the nickel atoms that had been trapped within. This temperature dependence is a crucial piece of evidence, pointing away from simple mechanisms like meteorite impacts and toward a more subtle chemical explanation. This leads the scientific detectives to two primary working theories. The first involves a process called photon-stimulated desorption. The Sun bombards the nucleus of 3I divided by Atlas with a constant stream of high-energy photons. This theory posits that the surface of the nucleus is made of compounds where nickel atoms are bonded in a chemically exposed or vulnerable way, while iron atoms are locked away in more stable, resilient mineral structures. The incoming solar photons act like a selective sandblaster, possessing just enough energy to chip the nickel atoms off the surface and into the coma, while being too weak to dislodge the more tightly bound iron. It is a plausible scenario, a chemistry of surface science operating on a cosmic scale. The second, and perhaps more elegant, theory connects this mystery directly to the other chemical anomaly we have already seen, the object's abundance of carbon compounds. This is the metal carbonyl hypothesis. In the ultra-cold, carbon-rich environment where 3I divided by Atlas was born, it is possible that nickel atoms chemically bonded with carbon monoxide molecules to form exotic compounds known as nickel carbonyls. These compounds are famously volatile. They can turn into a gas at very low temperatures. Iron, by contrast, does not form such volatile carbonyls under the same conditions. This theory paints a compelling picture. As 3I divided by Atlas warms ever so slightly on its approach to the Sun, it reaches the critical temperature where these nickel carbonyl complexes on its surface decompose, releasing their nickel atoms into the coma as a pure atomic gas. The iron, meanwhile, remains trapped in its non-volatile silicate and sulfide minerals, a prisoner within the rock, waiting for much higher temperatures that may never come. This theory beautifully intertwines two of the object's greatest mysteries, suggesting that the lonely nickel and the abundant carbon dioxide are two symptoms of the same underlying condition, a truly alien, ultra-cold birthplace. The interrogation of light continues. The detectives have their leads, and they are now watching the evidence evolve in real time, waiting for the object to reveal more of the secrets it carries from its distant, unknown home. There comes a point in any great investigation where the accumulation of anomalies becomes so profound, the coincidences so numerous, that the detectives are forced to consider a hypothesis that lies outside the bounds of their normal experience. When all conventional explanations for a phenomenon are stretched to their breaking points, the scientific method does not demand that we abandon the search. Instead, it grants us permission to widen the aperture of our inquiry, to cautiously, rigorously, and skeptically examine possibilities that might otherwise seem extraordinary. With 3I divided by Atlas, we have reached such a point. We have examined its impossible motion, its paradoxical appearance, its anomalous chemistry, and the improbable statistics of its very existence. And now, we must give a fair hearing to the most profound and consequential hypothesis of all, that 3I divided by Atlas is not a product of nature, but a product of intelligence. We must consider the case that it is an artifact, a probe, a piece of technology sent from another star. Let us enter the courtroom of scientific debate and first hear the case for the prosecution, the argument that this object is artificial. The evidence is entirely circumstantial, but the proponents of this hypothesis argue that its collective weight is compelling. They would begin with Exhibit A, the object's trajectory. Of all the infinite directions an interstellar object could have approached our solar system from, 3I divided by Atlas arrived on a path with an orbital inclination of just 4.1 degrees relative to the ecliptic plane. This means it is traveling along the same flat disk, the same cosmic highway that all the planets of our solar system use. For a random visitor arriving from an arbitrary direction, the statistical probability of such a convenient coplanar alignment is roughly 1 in 500. While not impossible, the prosecution would argue it is a deeply suspicious coincidence. Is it more likely that the very first massive interstellar object we have ever seen just happened to win this statistical lottery? Or that it was deliberately sent along the most efficient path to survey our solar system? Next, the prosecution would present Exhibit B, the core physical paradox of the silent giant. They would ask us to reconsider the evidence not as a mystery, but as a deliberate act. The mainstream explanation for the lack of acceleration is an immense, almost unbelievable mass. The technological hypothesis offers a different interpretation. The object is exhibiting controlled propulsion. The visible outgassing, the 150 kilograms of material being vented every second, is not a natural cometary process. Perhaps it is a form of highly advanced, low-thrust engine, one whose propulsive mechanism is so efficient that it produces no obvious thermal signature. Or perhaps, the prosecution would suggest, the outgassing is nothing more than a smoke screen, a deliberate release of gas and dust to make the object appear like a comet, a natural camouflage to disguise its true nature. In this scenario, the lack of acceleration is not due to immense mass, but because the object is actively and precisely correcting its own course, using its engines to counteract the recoil, and maintain a perfectly stable, predictable trajectory. It is not an inert mountain, it is a piloted vessel. Then, the prosecution would turn to the chemical evidence, Exhibit C, the mystery of the lonely nickel. They would acknowledge the plausible, natural explanations involving exotic carbonyls or photochemical processes. But they would also present an alternative. They would point out that the chemical signature of the gas-abundant nickel, with a conspicuous absence of iron, is strikingly similar to the composition of specialized, human-engineered alloys designed for specific magnetic or structural properties. While the observation is of a gas, this gas is sublimating from a solid surface. Is it not, the prosecution would ask, a remarkable coincidence that the one metallic element we see glowing so brightly is the key ingredient in many advanced industrial materials? It is another piece of the puzzle that, while not definitive on its own, adds to a growing pattern of unnatural-seeming characteristics. Finally, the prosecution would present Exhibit D, the curious timing of the object's journey. 3I divided by Atlas is scheduled to reach perihelion, its closest approach to the Sun, while it is on the far side of the Sun from Earth's perspective. This alignment creates a months-long observational blackout, a period when our most powerful ground-based telescopes will be completely blinded by solar glare. To the prosecution, this is not an accident of orbital mechanics, it is a sign of intelligent planning. What better way for a visiting probe to conduct its primary observations of the inner solar system, or perhaps to perform a major engine burn or change of course, than to do so while it is hidden behind the blinding light of our own star? In their closing argument, the prosecution would contend that while any one of these anomalies, the convenient orbit, the controlled propulsion, the strange chemistry, the evasive timing, could be dismissed as a natural, albeit rare, fluke, the combination of all of them together strains credulity. They would argue that the principle of Occam's razor, the idea that the simplest explanation is usually the correct one, might here favour a single, extraordinary cause, intelligent design over a collection of 4 separate, highly improbable natural events, all occurring in the same object. Now, we must hear from the defence, the voice of the established scientific consensus, a voice built on a foundation of skepticism and the demand for irrefutable proof. The defence would approach the evidence not with suspicion, but with caution. In response to the orbital argument, they would counter that this is a classic case of selection bias. We found 3I divided by Atlas because it was travelling along the ecliptic, where our surveys are most concentrated. We are like a fisherman who only casts his net in a single river, and is then surprised to only catch river fish. There may be countless other visitors on inclined orbits that we have simply missed. The 1 in 500 statistic is meaningless if the search itself is not random. In response to the propulsion paradox, the defence would argue that invoking alien engines is a far more complex and extraordinary leap than refining our understanding of cometary physics. Our knowledge of comets, especially a new class of carbon dioxide-rich interstellar comets, is far from complete. The lack of acceleration could be caused by a highly inefficient momentum transfer between the gas and the nucleus, perhaps due to the specific properties of the dust being ejected. The natural explanation of immense mass, while staggering, requires no new physics. It merely requires us to accept that our first encounter with a massive interstellar object has been, true to form, a surprise. The prosecution, the defence would argue, assumes intent where a simple gap in our knowledge is the more economical explanation. Regarding the chemical anomaly, the defence would dismiss the industrial alloy argument as unscientific conjecture that ignores the reality of the observation. The evidence is of atomic gas, not solid metal. The proposed natural mechanisms, such as the decomposition of metal carbonyls, are not only plausible, but are elegantly consistent with the object's other known property, its formation in an ultra-cold, carbon-rich environment. The universe is full of exotic natural chemistry. To see something unusual is not evidence of the unnatural. It is an invitation to learn. Finally, the defense would dismantle the idea of an evasive maneuver. The object's trajectory is not a choice. It is a destiny, one that was sealed millions of years ago and billions of kilometers away when it was first ejected from its home star. It follows the unyielding and predictable laws of gravity. Its perihelion timing is a pure, mathematical coincidence of celestial mechanics, no more suspicious than the chance alignment of planets in the sky. The defense's closing argument would be built on a single, powerful principle, the bedrock of scientific integrity. Extraordinary claims require extraordinary evidence. They would state that the prosecution has presented a compelling list of puzzles, of anomalies, of deep and fascinating scientific questions, but they have not presented a single shred of positive, extraordinary evidence. There has been no verified, coherent radio signal. There has been no detection of unnatural, non-thermal emissions that would indicate a power source. There has been no unexplained, sudden trajectory change that would indicate a major engine burn. And there is certainly no resolved imagery of a manufactured object. Until such evidence emerges, the scientific default position, the only responsible position, must be that the object is a product of nature. The courtroom is at an impasse. One side presents a pattern of circumstantial evidence that is deeply suspicious. The other demands a standard of proof that has not yet been met. How, then, can a verdict be reached? The answer may lie in a final, audacious proposal to move beyond this long-distance debate and send a detective to the scene of the crime. Multiple research papers have outlined a technically challenging, but potentially feasible, mission to redirect NASA's Juno spacecraft, currently in orbit around Jupiter, for a close encounter with 3I divided by Atlas as it passes by in March of 2026. Such a mission represents the one and only opportunity to settle this debate. A close flyby could provide the kind of extraordinary evidence that both sides agree would be definitive. It could capture images of the nucleus, revealing whether its surface is a natural landscape or an engineered structure. Its instruments could directly sample the gas and dust of the coma, searching for isotopic ratios or chemical compounds that are unambiguous biosignatures or industrial byproducts. The decision of whether to attempt such a mission has elevated this debate from the halls of academia to the halls of Congress. The verdict on 3I divided by Atlas is not yet written, and humanity is now faced with the choice of whether to remain a passive observer or to take a bold leap and seek the truth for itself. Beyond the courtroom of competing hypotheses, beyond the binary choice between a natural anomaly and an artificial artifact, there lies a third path. It is a concept of such elegance and scope that it reframes 3I divided by Atlas not as a puzzle to be solved or a threat to be feared, but as a potential architect of worlds. This idea suggests that the greatest mysteries are sometimes solved not by looking deeper into a single problem, but by realizing that two seemingly unrelated problems are, in fact, two halves of a single, beautiful solution. For decades, the story of how planets form has been a grand epic, but one with a frustrating and persistent plot hole. And the recent discovery of massive interstellar wanderers, like 3I divided by Atlas, may be the missing chapter that finally makes the entire narrative whole. Let us first tell the traditional story of creation, the story of how a gas giant like our own Jupiter is born. It begins in the swirling, primordial disk of gas and dust around a young star. In the beginning, there is only dust, microscopic grains of silicate and ice. Through electrostatic forces, these grains begin to stick together, forming fluffy aggregates. Over thousands of years, these grow into pebbles, which then coalesce into boulders, and then into kilometer-scale bodies we call planetesimals. It is a slow, grinding, bottom-up process of construction. The goal is to build a solid core of rock and ice, perhaps 10 times the mass of the Earth. If a core can reach this critical size, its gravity becomes so powerful that it triggers a runaway process, pulling in vast amounts of the surrounding hydrogen and helium gas from the disk to form a thick planetary atmosphere. This is the final step to becoming a gas giant. But this entire process is a desperate race against a ticking clock. The antagonist in this creation story is the very star that gives the system life. A young star is fierce and energetic, blasting its surroundings with intense radiation. This radiation actively works to destroy the protoplanetary disk, heating the gas and blowing it away into interstellar space. This process, called photoevaporation, is ruthlessly efficient. A typical disk of gas and dust lasts for only 5 to 10 million years before it is completely dissipated. This is an incredibly short window in cosmic terms. The slow, bottom-up process of building a planetary core from dust must be completed before this deadline, before its primary food source of gas is taken away. And for years, our models have struggled to win this race. They are plagued by a particularly vexing villain known as the meter-sized barrier. Objects that grow to about a meter in diameter experience a strong headwind from the gas in the disk. This aerodynamic drag causes their orbits to rapidly decay, and they spiral into their parent star in a cosmic death dive, often in less than a century. This barrier acts as a great filter, making it incredibly difficult for pebbles to grow into planetesimals fast enough to form a giant planet's core before the clock runs out. The epic story of planet formation has been stalled in its first act, in need of a hero. Now, let us open the second book, the new and mysterious story of interstellar visitors. What if the hero did not have to be built from scratch within the system? What if it could arrive, fully formed and battle-ready, from a distant land? This is the core of the planet seeding hypothesis, a concept championed by theorists like Suzanne Faulkner. It proposes that interstellar objects like 3I divided by Atlas could be the solution to planet formation's timing problem. Let us imagine the scene. A young star is surrounded by its massive, gas-rich disk, struggling to form its own planets. Into this system plunges a wandering mountain, a 5-kilometer, 33-billion-ton object that was forged in another solar system and ejected millions of years prior. For the small, meter-sized bodies native to the disk, the gas is a deadly trap. But for this massive interstellar visitor, the gas is a welcoming cushion. The drag is still there, but because the object possesses such immense mass and momentum, the gas is not strong enough to make it spiral into the star. Instead, the drag acts as a gentle brake, bleeding off the object's hyperbolic excess energy, circularizing its orbit, and capturing it as a new, permanent member of the solar system. The visitor has been captured. The wanderer has found a new home. And it is not just a visitor. It is a seed. It arrives with a colossal head start in the race against time. It is already a multi-kilometer, fully formed planetary core. It has completely bypassed the slow, grinding process of building from dust. It has leaped over the deadly, meter-sized barrier. This captured seed, this interstellar hero, is now in a perfect position to begin the final act of creation. Its immense gravity immediately begins to anchor the surrounding gas and dust of the disk. The runaway accretion process, which might never have started for a homegrown core, can now begin immediately. The gas that was destined to be blown away by the star now has a new, powerful, gravitational anchor to cling to. A gas giant can form, and it can form quickly, well before its 10 million year deadline expires. This hypothesis is not mere speculation. It is a compelling framework that is beautifully consistent with the strange properties of 3I divided by Atlas. The very quality that makes it a physical paradox. Its immense mass is the exact prerequisite for it to act as a viable seed. A smaller object like Borisov might be captured, but it would not have enough gravity to jumpstart the formation of a giant. The object's alien chemistry, its high concentration of carbon dioxide, also fits perfectly. A captured seed would be, by definition, an outsider, composed of materials from a different stellar environment. As it becomes part of the new system, it would introduce this chemical diversity into its host disk, potentially explaining some of the surprising and varied atmospheric compositions we are now discovering in exoplanets. Even the statistical puzzle of the elephants finds a new light. If these massive interstellar objects are not just rare curiosities, but are in fact a vital catalyst in the formation of the most common type of large planets in the galaxy, then perhaps the universe has a vested interest in producing and distributing them more efficiently than our earlier models suggested. The planet seeding hypothesis does not just solve a problem in planet formation. It reframes the entire question of interstellar demographics. If this idea is correct, its implications are profound, extending far beyond a single object or a single solar system. It suggests that the galaxy is not a collection of isolated, island universes. Instead, it is a single, vast, interconnected ecosystem. It operates on a grand cycle of creation, death, and rebirth. The material forged in one stellar system, when it is mature or dying, can be ejected and become the literal seed for new creation in a young system halfway across the galaxy. Stars become the trees of a galactic forest, and massive interstellar objects are the seeds, carried on the slow cosmic winds from one part of the forest to another, finding fertile ground in the swirling nurseries of new stars. It suggests a form of galactic communication, not of intelligence or information, but of matter and potential. The universe, it seems, recycles. The story of our own solar system may have been influenced by such a visitor billions of years ago. The core of our own Jupiter might contain within it the frozen, chemical memory of a star that died long before our sun was ever born. This hypothesis remains a theory, a beautiful and elegant story awaiting the confirmation of more data. As the Vera Rubin Observatory begins its decade-long survey, we will finally have the statistics to test it. If we find that massive 5-kilometer interstellar objects are indeed common, then the case for planet seeding will become incredibly strong. For now, it offers a new identity for our mysterious visitor. 3I divided by Atlas may not be a monster that breaks the laws of physics or a machine sent by an alien civilization. It may be something far more profound. It may be a creator, a bringer of potential, a cosmic Johnny Appleseed carrying the promise of new worlds from one star to the next. There is a question that hangs over the entire saga of 3I divided by Atlas, a puzzle that is not written in the language of physics or chemistry, but in the language of time itself. Why now? For the entirety of human civilization, for all the millennia that we have looked to the heavens, the space between the stars was a realm of myth and conjecture. Then, within the span of a single decade in the 21st century, our solar system has seemingly become a crossroads for these mysterious travelers. First ʻOumuamua, then Borisov, and now the giant Atlas. Is the galaxy suddenly sending us messengers? Has some ancient cosmic cycle reached a new phase, filling our neighborhood with an influx of visitors? The cosmic timing puzzle is a tempting invitation to seek grand, external explanations. But the truth is more profound, and it is found not by looking out at the stars, but by looking inward, at ourselves. The universe has not changed. We have. We have, in the span of a few short years, built ourselves a new set of senses. To understand this revolution, we must first appreciate the blindness that preceded it. For most of the 20th century, discovering an interstellar object was a matter of sheer, unadulterated luck. An astronomer, manually inspecting a photographic plate for something else entirely, might happen to notice a faint smudge that was moving too fast on too strange a path to be a member of our solar system. Such an event was a statistical miracle. The surveys of the time were piecemeal, their cameras were small, and their sensitivity was limited. They were like fishermen with tiny nets in a vast ocean, hoping for a whale to swim directly into their grasp. The chances of catching these faint, fast-moving visitors were astronomically low, not because they were not there, but because our tools were simply too primitive to perceive them. The story of why we are finding these objects now is the story of a perfect storm, a confluence of technological and intellectual advancements that have collectively given our planet a new awareness of its cosmic environment. The first element of this storm is a revolution in hardware. We have built bigger, better eyes. The discovery of 3I divided by Atlas was made by the Asteroid Terrestrial Impact Last Alert System, a network of robotic telescopes. The name itself is telling. Its goal is to scan the entire visible sky every few nights, a task unimaginable just a generation ago. And the network itself is new. The Southern Hemisphere component in Chile that made the initial detection only began its full operations in 2022, completing a global, all-sky watch. These are not traditional telescopes that peer at a single star for hours. They are ravenous machines, equipped with enormous wide-field cameras and highly sensitive digital sensors that gulp down vast portions of the heavens in a single exposure. This technological leap has transformed our search from a hopeful glance into a systematic, relentless stare. But these new eyes would be useless without a brain capable of interpreting what they see. The second element of the storm is a revolution in software and data processing. A facility like Atlas produces a torrent of data so immense it is beyond human comprehension. A digital flood of petabytes. Within this flood are the faint signals of these interstellar visitors. The true discoverer of 3I divided by Atlas was not a person, but an algorithm. Sophisticated software tirelessly compares every new image of the sky with previous ones, searching for those single points of light that have moved against the fixed backdrop of stars. It is a search for the tiniest of anomalies in a universe of data, a task that software can now perform with incredible speed and accuracy. This automated brain is then connected to a nervous system, a rapid response pipeline. When the algorithm flags a potential object of interest, it does not sit in a database for weeks. An alert is automatically sent out to the global astronomical community within hours. This speed is the critical link. It allows the world's most powerful follow-up facilities, the deep gaze of Hubble, the infrared vision of the James Webb Space Telescope, the forensic spectrographs of the Very Large Telescope, to be trained on the target almost immediately. This rapid coordination is the difference between getting a clear, detailed portrait of a visitor and catching only a fleeting, blurry glimpse as it disappears back into the darkness. Even with this new planetary nervous system, luck still plays its part. The third element of the storm is the favorable geometry of this particular encounter. 3I divided by Atlas, as we have seen, arrived on a trajectory nearly aligned with the ecliptic plane, the highway where our planets travel, and where our survey telescopes spend most of their time looking. This convenient path made it intrinsically easier to spot and to track for an extended period. It was discovered at a sweet spot in its orbit, giving us a long, multi-month window to perform the high-precision astrometry needed to unveil its paradoxical nature. Had it arrived on a trajectory plunging down from the pole of the solar system, or had it been discovered much closer to the Sun, our window of opportunity would have been vastly smaller, and its greatest secrets might have remained hidden. So, the cosmic timing puzzle is not a single question, but a convergence of answers. We are finding these objects now because we have finally built the hardware that is sensitive enough to see them. the software that is smart enough to find them, and the collaborative networks that are fast enough to characterize them. And in the case of 3I divided by Atlas, the universe presented us with a visitor whose path was convenient enough to make the full power of this new system shine. The visitors were likely always passing by. We were simply blind and deaf to their presence. Now, for the first time in the 4.5 billion year history of our planet, one of its species has developed the senses to perceive them. This revolution is not over, it is accelerating, and we can see its next phase in the unique opportunities presented by our own robotic emissaries already in space. As 3I divided by Atlas approaches the Sun, it will enter a period where it is lost to our view from Earth, hidden in the glare of our star. But we have an eye in a place no human has ever been. NASA's Parker Solar Probe, a spacecraft designed to touch the corona of the Sun, will be in a perfect position to observe the visitor during this blackout period. From its unique vantage point, it will have a side-on view, a completely different perspective that may be able to resolve the mystery of the sunward glow and watch the object's activity evolve under the most intense solar heating. This is another capability we have acquired only in the last few years. Another tool in our arsenal that allows us to piece together a more complete picture of these travelers. We are no longer just inhabitants of the solar system. We are becoming its watchmen, finally aware of the great interstellar traffic that has been passing by in silence for all of human history. This revolution in astronomy is happening in our lifetime, and we are all witnesses. What are your thoughts on this pivotal moment? Which of the bizarre characteristics of 3I divided by Atlas do you find most compelling? We would love to read your perspective in the comments below, as this global conversation is shaping our understanding of the cosmos in real time. If you want to continue on this journey and stay at the forefront of this incredible new era of discovery, consider joining our community by subscribing. History is being written, and it is a privilege to witness it together with you.